Good afternoon, everyone in Taiwan, and good morning to Maxime in France. Today is my great pleasure to have our speaker, Professor Maxime Breden from École Polytechnique. I am not very good at pronouncing this. Okay,
That's good.
but okay, today he will give us a lecture, introductory lecture, including his recent research about the computer assistant proof for dynamical systems. And here you see how a numerical simulation can be transformed into a theorem. I think this is a very important technique tool, and of course, we are very curious about this. So let's welcome Maxime.
Well, thank you very much for the introduction and also to the invitation. And let me repeat to everybody what I say to Chair One before is that please, even though this is not an in-meeting person, feel free to interrupt, ask questions, and I will be happy to make the talk as interactive as possible.
Yes, yes.
So let me first set the stage maybe by telling you what kind of computer-assisted proof I want to do, because there are actually many different things that are called computer-assisted proof that are quite different. So the type of computer-assisted proof I'm going to tell you about today is the one where you try to prove quantitative theorems about some specific solution of a given mostly ODEs or PDEs in my case, but you could think about different dynamical systems using numerical simulations. So what I mean by quantitative is that I'm not only interested in the existence of a solution. Sometimes existence is already very hard and very interesting, but sometimes also would like to know more precisely what the solution looks like, what kind of properties it has. And also specific because I'm not going to try and solve, let's say, initial value problems where I say, okay, for every initial data in this or that function space, there is a solution. But instead, I will look at some specific solution, the easiest thing being steady states, but maybe also then periodic orbits or invariant manifold attached to those traveling waves, these kind of things that are hopefully relevant for understanding the global dynamics of the system. So as I said, either you care about these specific solutions because they are interesting in and out of themselves. I mean, apparently, Olivier gave a talk to at least to some of you yesterday where he talked about figure 8 in celestial mechanics. This is a good example of a specific solution which has been very interesting to many mathematicians before. Or those specific solutions, you view them as a organizing block for the global dynamics. Okay? And typically, we'll show you examples where you would like to prove the solution exists and say what it looks like, and by hand you, at least I don't know any way of doing it, but then combining numerical simulation and then the computer assisted proofs, you can sometimes do this. And I will give you a few more references during the talk, but I want to already emphasize that even though computer assisted proof seems very recent, and okay, to some extent it is, some of the ideas I'm going to present, they really go a few decades back already, and especially to works by Lanford on the Feigenbaum conjecture. Okay, so here's the outline. We will first start with a simple, very simple dynamical system, very simple example where I can show you all the steps for a successful computer-assisted proof. And then we will discuss how we can generalize these ideas. And then I won't have time to go through all 3 examples probably, but depending on how much time is left, we will discuss 1 or 2 of them. Okay, so here is the example. So as I told you, it's very simple. I mean, you can hardly do more simple without being completely trivial. So we're going to look at this sequence. Xn plus 1 is mu times xn times 1 of minus xn, when mu is some parameter between 0 and 4. So some of you, especially if you come from dynamical system, you might be very familiar with this logistic sequence already. If you're not, let me maybe remind you what this sequence does by showing you first a simulation. So here okay, wait. Yes. Here I plot for you the first 60 iterate of that sequence when the parameter mu is going to change for the moment it's equal to 1. And there it's very boring. Apparently the sequence converges to 0. And of course you could prove that. You could ask your undergrad to prove that as an exercise. It's not hard. But then what happens when the parameter mu changes? So at first, when you change mu, the sequence still converges, it just converges to something else. And this is still easy, you could still prove it by hand very easily. But then when you keep increasing the parameter, the dynamics starts becoming more interesting. And at first you see this behavior where apparently the sequence oscillates between two different values. So this apparently is a period to orbit for the system. And when you keep increasing the parameter, then you apparently see a period 4 orbit. And if I were to keep increasing very precisely now the parameter, I would see a period 8 orbit and so on. And if you keep increasing, after a while, you see this kind of erratic behavior. It's hard to make any sense of what you're seeing, even though this is still the very simple sequence I showed you at the beginning. Okay. So this is a typical example of even though the system itself, so this dynamical system is very simple looking, the dynamics it generates is complicated. And this is typically how one summarizes and all this kind of simulation I showed you. So on this graph, on the x-axis, you have the value of the parameter mu. And on the y-axis, what you see, every time you see a gray dot here, it's because there is an accumulation point of the sequence. So on the left, apparently for mu less than 3, we have only one accumulation point. So this indeed corresponds to what we saw when the sequence converges. Then you have two accumulation points. So you have the period to orbit, period 4 orbit, and here to the right, you have these regions, where apparently the sequence goes all over the place. There are accumulation points almost everywhere, which is a bit what we saw on this picture, right? And so maybe you would like to to understand this better and to quantify a bit these complicated dynamics here, and to prove that in some sense there is a lot of complex dynamic, a lot of different solutions that can appear when mu is close to 4. And there is actually a well-developed mathematical theory for that, which is not going to be the main focus of this talk. It's just the notion of chaos. And so the only thing I will be using about chaos here, and I'm just recalling it here, is this very famous theorem, which I've cited not super precisely, but which tells you that for any map, any sequence, xn plus 1 is f of xn, where f is just a continuous map from an interval into itself. If you find one orbit which is of period 3, then you have in some sense chaos. And again, I'm not going to be very precise about chaos, what chaos means here, but at least it implies that you have existence of infinitely many periodic orbits of any period, and also some kind of sensitivity to initial data. Okay. So that's a very beautiful theorem, also completely pen and paper theorem, of course. But when it gets a bit complicated is when you want to actually apply this theorem. Right? Suppose that I take mu equal 3.9, because when I look at the simulation, when mu equal 3.9, the dynamics is complicated. I would like to be able to say that it's chaotic in this sense. If I want to apply the theorem, I need to find and prove the existence of a period 3 orbit. Okay, and this is maybe not so easy. So actually, not completely true, because for this specific system, this system is simple enough that you could prove this by hand. But this is a typical example of why you would like to use computer-assisted proof. You have these very beautiful abstract results that tell you for your ODE or your PDE, if you find one solution with those specific properties, then this and that happen. But then finding the specific solution is really hard. And so here, what we are going to do in the first part of the talk here is I will show you how you can use computer-assisted proof to prove existence of a period 3 orbit for this sequence. And I'm not claiming, as I said, that this is the only way of doing it, but at least the way I'm going to show you, then most of the ideas, they generalize to more complicated problems. Okay. So the first step to prove that a period 3 orbit exists is maybe, okay, to convince yourself that there is one. So you might want to start doing some numerics and then see if you find the period 3 orbit. And again, there are different ways of doing that. One way of finding numerically a period 3 orbit, which is maybe not so sensitive to whether this orbit is actually attractive or repulsive, is to first rewrite the problem slightly and consider this map, F from R3 to R3. If you look at it for 5 seconds, you can probably convince yourself that if you have a 0 of that map, then x1 is indeed the image of the first of x0 by the sequence, x2 is the image of x1, and then the image of x2 itself is back to x0. So provided the three x0, x1, and x2 they are different, a 0 of f is really a period tree orbit for your system. Okay. And then numerically, you just have to find a 0 of a map from R3 to R3. So you use, for instance, Newton's method, and that's easy. Okay. So indeed, let me show you. This is really very easy. So I did this in a, I implemented the map, I implemented the derivative. For the moment, the derivative is simple enough. I can compute it by hand. At some point, this will no longer be the case, but okay. And then I just do Newton's method with an initial guess, which is just random. Okay. And this is what I see. So here are the errors. So you see the quadratic convergence that you expect from Newton's method. And here is apparently a numerical 0 of that map. So this would be x0, x1, x2. And okay, the numerics are rather convincing. So it looks like there is a period tree orbit, but how can we prove it? Yes, because if I want to claim I have proven there is chaos in the system, I cannot only say, yeah, numerically I found something. I need to prove the solution is there. And so somehow this is a very general question now. You can forget a bit about where the map F comes from. You have a map from Rn to Rn. Later on, it will be between an infinite dimensional Banach space and, well, you want to solve your ODE or your PD. And I have an approximate 0. So typically a numerical solution that I found. And how can I prove that next to this approximate 0, there is an exact 0 of the system? Okay. So you want to do some kind of a posteriori analysis where you prove the existence and then you also get an error bound. And for that, you can use this kind of Newton control ridge theorem, which if you've heard about computer-assisted proof before, you must have seen at least a different version of this, probably. So let me briefly recall this, what this theorem is about. So this is essentially the constructive version of Newton's method, which tells you precisely how close to a 0 you have to be sure that there is actually a 0, right? So this theorem tells you that if the residual error, which is controlled by epsilon, is small enough, and it makes it very explicit what small enough is in terms of the inverse of the Jacobian at the numerical solution and some kinds of Lipschitz bound on the derivative, then you have a unique 0 of f close to x bar, and you have an explicit error bound in terms of those estimates. Okay. And the proof of this is really not hard. It's just applying the contraction mapping theorem to this Newton-like operator. Okay. So again, here the theorem itself is not hard. In practice, what may be somewhat difficult, even though for this easy example it's not, is to find the explicit bounds epsilon, kappa, and L satisfying those assumptions. Because you cannot only say, okay, there exists a kappa such that this is finite. You have to find it because you need to check this assumption. And at least for some of them, the epsilon, you have to find reasonably sharp bounds. Otherwise, you're not going to satisfy this inequality. But for this problem that I showed you before, it's very easy. And I just did it here. So one ingredient that I need was the inverse of the derivative at the solution. Here again, it's still easy enough that I can compute the inverse by hand. So I just did it, I implemented it here. And then we compute. So epsilon, let me remind you, epsilon should be an upper bound of the residual error. Then kappa, an upper bound of the norm of the inverse of the Jacobian, and then there is a Lipschitz constant. So for epsilon, I just took the norm, the residual error. I mean, you need to choose one norm here. I took the one norm. For kappa, I take the norm of the inverse, which is here. And then for L, you just do a small computation by hand. I mean, the map is only quadratic, so the Lipschitz constant of the derivative is really just a global number. You can compute it by hand. You can trust me, it's 2. And then I check. this condition epsilon small enough is satisfied or not. Okay, sorry. And so here is the output. I have epsilon really small, kappa and L, which are some numbers, and then indeed epsilon is smaller than 1 over this thing. And so I have a proof, and I have an error bound. Okay. So are you maybe all convinced or not convinced that I have actually proven the existence of a period tree orbit? Is this fully a proof?
I think so.
Yes.
Yes. Conjecture. I trust conjecture mapping argument.
Yes. So do I. But
yes.
am I really sure? So in the assumption of the theorem, I need epsilon to be an upper bound for the norm of the residual error, right? And what did I do? I took the residual, I computed the norm numerically with here MATLAB, but okay, it doesn't matter that it's MATLAB.
I see.
And I have a number.
Okay.
So this number is indeed close to being an upper bound, but I mean, those are floating point computation, right? It could be that epsilon is a bit smaller, actually, than the residual error and not larger. So, of course, the epsilon is really much smaller than this thing, so it should be fine. But still, I'm not entirely confident saying it's a proof yet, because of this epsilon and this kappa, they are just obtained with floating point arithmetic. And even though for this example, I'm fairly confident, if I want to do something similar later on more complicated systems on Navier-Stokes, let's say, or when there are a lot of computation involved, then I better make sure that when I compute this estimate, the rounding errors, they are under control somehow.
Okay, I see. Yeah.
And okay, sorry. Maybe you think I'm exaggerating that, okay, this floating point error, they cannot be that bad. Okay, so depending on whether you have some experience with numerics or not, or you might think that's fair. So I will try to convince you now that even though in the end these floating point error are not going to be a problem for us, you still have to be careful. So for that, we will look at this this function g of ab, which is almost a polynomial with there are some rational entries and just a fraction here. So this is a famous example that was introduced by Siegfried Rump in the 90s. So, and we're going to evaluate this thing with two integer entries, which are a bit large, but also not super large, and see what is the output. And pretend for the sake of the example that I have a theorem that says that if g of ab for those specific a and b is positive, then something happens. Okay. So then, okay, numerically, I will want to check, compute g of ab and see what happens. So here it is. And just so you know, I mean, in principle, when you do powers, depending on your language and you're not always sure what's going on. Sometimes actually the program is doing the exponential of the log or something. And so here to be sure, when I see b to the power 6, I really implemented b times b times b times b 6 times and so on, just to make sure that there are the only errors that are here are errors related to multiplication, addition, subtraction, and division. Okay. And so I'm evaluating this g for these entries a and b that I showed you before. Okay. And so here for the moment, I'm telling MATLAB, okay, do the calculation with roughly 8 digits of precision in base 10. And this is what I get. But okay, I really want to prove a theorem. I want to be sure that it looks positive, but I want to be sure it's positive. So I'm doubling the precision, right? This is also in some sense, sometimes what we do when you do numerics, you find a solution, you refine the grid or something, and you do the simulation again. And if the output doesn't change, your confidence. Yes. And indeed, it looks very reasonable. Apparently, it was even rounded correctly the first time. But okay, we want to be really, really sure. So let's increase the precision even more. Yes. Okay. Still fine. So now probably you would be willing to state very convincingly that okay, g of ab is indeed positive. Yes. But in fact, if I keep increasing the precision, this is what I get.
Yeah.
Unfortunately, this is the correct answer, up to maybe the last digit or something. Okay. So here the rounding errors, they really got me into trouble until I had enough precision. And there was no way of guessing it. Even when by being careful and by just increasing the precision a bit, I couldn't see the problem until I had high enough precision. Okay. So how can I be certain that this is not happening when I check the assumption of my theorem, right? That's I need to be sure these kind of things are not there, right? And so for that, fortunately for us, there is a very easy way of getting around these things. Is by using what is called interval arithmetic. So I will, in 2 minutes, recall you what interval arithmetic is. And if you, especially some of the locals, you have more questions at the end, you can ask me, but of course you can also ask Olivier, who is more an expert than me on those things, especially on the concrete implementation side. So the only thing you need to know to understand interval arithmetic is to remember that the computer, it cannot store any real numbers. It can only deal with finitely many of them. So we will call F the finite set of numbers that the computer can deal with. And there are two operations that the computer can do and will do when he deals with numbers. It's rounding up and down, meaning that whenever you take a real number, even though the computer may not be able to represent it exactly, it can give you the closest representable number, which is just above or just below it. Those are this operation. And so as an example, when you type x equals 0.1.1 in your favorite language, actually what happens is, of course, it's first turned into base 2 because the computer works with base 2. And then in base 2, 0.1 is unfortunately not, doesn't have a finite expansion in base 2. It has infinitely many digits where this 1100 block is repeated. And so the computer cannot deal with that. It has to truncate. And so if we pretend for the sake of the example that we take 8 digits of precision, then the rounding down version of 0.1 is this number when I just take 8 digits and then I truncate. And the rounded up version is this one when I take 8 digits and then I increase the last one. Okay. So this is what's happening every time when you do floating points computation. And what is interval arithmetic is to say that instead of replacing a real number by a floating point number, which is indeed at first very close, but whether it's larger or smaller than the real number, you don't know. And then when you do operation, you don't keep track of everything. You instead represent a real number by an interval, which contains the real number. Okay. So really the crucial property is that the number you care about is inside this interval. And then you have to extend all the basic arithmetic operation in such a way that when you add stuff or divide them or multiply them, you still keep the correct value inside. So for instance, when you add two intervals, how should you do it? Well, you should add the lower bounds together and then round them down. And then on the other side, add the upper bounds and round them up. And this way, it's guaranteed that the true real number x plus y is actually inside that interval. And then, okay, maybe not 100% obvious that the computer can do it, but it can. And then, and of course, you don't have to do everything, all of this yourself, right? There are libraries in many languages that do that for you, not only for addition, but for all elementary operation, and then for all kind of function, cosine, exponential, or more fancy special functions. So this, you don't have to do it yourself, but it exists and you can use it if you need to. Yes. And so let's see on our example what this does. So here I'm using IntLab, so it's a toolbox for MATLAB that does this thing. And so what I can do here is take this. So x is A and B, two values. and I can declare this to be an interval. So it's not a, it's actually a vector of 2 entries, and each entry is an interval. Of course, these entries, they're integers, so the computer, it can represent integers exactly. So they are interval of with 0, both of them, for instance. The lower bound is equal to the upper bound. But since this is now declared as an interval, every computation I'm going to make now is going to be done using these rules of interval arithmetic. Okay, and so when things are not representable exactly anymore, we will use these things, and we will get at the end an interval that contains the true result. Okay, so let's see what we get. Okay, so the computer tells me that the answer is between -8 times 10 to the power 21 and 7 times 10 to the power 20. So this is, of course, completely useless, but it's true. Okay, and at least I know that something fishy went on here and that I should not trust the result. Okay, so interval arithmetic is not going to fix the problem for me, in the sense that here there are very bad cancellation errors in the calculation, and if they are there, the precision is lost. There's nothing we can do about it. But it's warning us that this is occurring. And the main message I want to convey is that in general, you should not worry too much about floating points error. They are not going to be a problem unless you are doing something very specific. And interval arithmetic just allows you to check a posteriori that nothing wrong happened. Okay, here the problem is that I took a very specific example and it's very specific value of x. But if I change the input a little bit, so the a and the b, I'm just going to shift them not by much. So here are new a and b's which are not too far away from the one I had before. And again, I'm turning this into an interval, and I'm computing g. Yes. And here you get a number, you cannot even see the interval, so maybe I need to show more digits for you. And so here I'm asking the program to show me the infimum and the supremum of the output. Okay. So I change slightly the input result, and here I get something which is really reasonable. I mean, probably the first 10 digits or so are the same. So in relative error, this is really a small mistake, right? And this is what you typically expect, in fact. Okay. Of course, I mean, many of us, we do numerics with floating points and we don't have problems. So floating points in many cases are fine. It's just you need to be able to be sure that nothing wrong happened. And with interval arithmetic, you can at the end. And so let's do that for our example. So we go back to this proof I had before. And I do exactly the same thing, except at the beginning, I declare that the parameter mu is an interval. And my solution, so the solution x is still obtained by doing Newtons with floating points. You should not change arithmetic at that level. But once you have the approximate solution, then you say, okay, I declare this as an interval so that all the computation for the bounds, epsilon, k, and l, they are done with intervals. And then what I get is an interval for epsilon, okay, when I compute the norm. And then if I go back to my theorem, if I compute this and I get an interval which contains this result, then I just can take the upper bound of that interval and it will satisfy this assumption. Same thing for kappa, same thing for L, and then I can do things rigorously. And this is what I've done here. Okay. So let's look at the output again. So this was the epsilon with floating points, and this is the epsilon with interval arithmetic. So it's not that much larger, but this one is guaranteed, whereas this one was not. Okay. And then I get almost the same result with a very small upper bound. Okay. And here I'm confident claiming this is a proof. And of course you need some interval arithmetic library, but once you have it and you just use it, it doesn't change much in the code in the program, right? So it's actually something. This is not the big deal about computer assisted proof. It's just you need to know that this exists and you can use it.
Yeah.
All right. So yeah, this I just explained. So let's maybe summarize what we did on this simple problem, and then we discuss how we can generalize this to more complicated problems. So we wanted to prove that there was a period 3 orbit in that problem. And so we first turned that into finding the zero of some function. Then we found numerically an approximate solution, an approximate zero, by here Newton, but it could be whatever method you like. Maybe the problem is difficult, you need to select a well-adapted numerical method for your problem. And then you estimate a posteriori these three quantities, okay, which were the one in my theorem. So here the L I had before, I just replace it by the second derivative. That's the same. And only at this stage you have to be careful and use interval arithmetic and not before. Okay. And then you combine everything into this fixed point theorem to apply the contraction mapping and say that you have a fixed point of t and therefore a zero of f close to x bar. Okay. And so what I claim, and I'm trying to convince you, I'm going to try to convince you now that this is really, most of these ideas actually they generalize, and some they become a bit more complicated, and then we are going to discuss what to do with them. So in general, it generalizes, but then you have to make choices, right? If you think about your favorite ODE or PDE, and you have a specific solution in mind that you care about, there are probably different ways in which you can turn this into a zero finding problem. Different ways in terms of the algebraic formulas, but then also different spaces in which you could try to solve the problem, different norms and so on. And then at that stage, it's not at all different from a usual pen and paper proof for PDEs. I mean, choosing the right norm is important. Choosing the right space is important, and for us, it's the same. Yes. And you need also to find an approximate zero. So this I'm not going to discuss too much, in fact, in this talk. It can be hard, but I'm assuming that either I can do it or somebody else can do it and give me the approximate solution. And then I use it. Okay. And then you need to estimate a posteriori these three quantities. And I'm not going to give you so much details, but what I claim, and maybe with some of the examples it will become a bit clearer, is that the first one is usually not the problem. Of course, it depends a bit on how you do the numerics, but at least in the examples, I will show you concrete examples later when this is not an issue. Okay. The last one, well, this one is a bit more difficult if you want to get a very sharp estimate, but you don't really have to. This is only to say, okay, close to x bar, how nonlinear the problem is. This was what was called L in the previous theorem. And okay, you need to find an explicit L, but it doesn't have to be the sharpest possible. This is not so important. And in that sense, just getting an explicit estimate is usually not too bad. But the bad guy is this one, okay? Because now in general, we are in infinite dimension. Typically your function space you're going to solve the problem is infinite dimensional. You don't know a priori that this derivative at the numerical solution is invertible. So even proving that the norm is, that this object is well defined and the norm is finite is not trivial. And you have to find something explicit, right? And even though this is just, it's the inverse of it's just a linear operator, it might depend in a very complicated way on x bar. And x bar is not something like you have an explicit formula for it. And if you had an explicit formula for a good approximate solution, then you don't need a computer-assisted proof usually. But the point is that we want to use this in situation when it's not a perturbative argument where we are close to bifurcation or close to an asymptotic regime where we know something. It's typically you want to use these techniques where you know nothing about the system, or at least not locally. And so x bar is just a bunch of numbers of, for instance, Fourier coefficient or finite element coefficient that sits on your computer. And still you need to control this norm of the inverse. And so this is a bit difficult. But it's not impossible, and I'm going to try to give you ideas how you do that. So in the literature, there are actually at least two rather different approaches that allow you to do that. So the first one is especially useful when the problem or the Fréchet derivative is actually self-adjoint, and you are working in Hilbert spaces. Because if you have a self-adjoint problem and you are working in Hilbert spaces, then the norm of the inverse is just 1 over the smallest eigenvalue, or the 1 over the modulus of the eigenvalue that is the closest to 0. Okay. And so in some sense, these estimates, you can then turn it into getting rigorous enclosures of eigenvalues. So which is also not trivial for infinite dimensional problems, but there are existing techniques, especially developed by Plume, but also by other people especially in Japan, that allow you to do that. And so in some cases, you can get rigorous eigenvalue bounds and then turn that into a rigorous error bound. Here I'm going today to present you a different approach, which is, okay, it has pros and cons compared to the other one. One of which is that you don't require a Hilbert space. And the other one is that sometimes it's a bit easier to use in practice and also easier to explain. I mean, the other one I would need another talk probably to explain it to you. So what's the idea here? The basic idea is very naive, in fact. You say, okay, pretend we're lucky and that the Fréchet differential at the solution is not too far away from identity. If that's the case, in the sense that its norm is strictly less than 1. If that's the case, we know it's invertible and it's just a Neumann series argument that's saying that you can write explicitly the inverse and you have a bound. Of course, this is very restrictive. I don't want to assume this is true because otherwise there are so many problems I cannot deal with this. In many cases, this is not going to be true. But this idea, it can be salvaged somehow just by using, so depending on your background, you might think of it as an approximate inverse or maybe as a preconditional, in fact. Okay. And instead of looking at identity minus df of x bar, I'm going to try to find a linear operator A such that identity minus A times df of x bar is small. Because if I find such an A and A is injective, then I can still show that df is invertible at x bar, and I have a bound on the norm of the inverse, which is the same factor as before times the norm of A. Okay. So this estimate tells me that indeed df of x bar is invertible and that A is not too far away from being the inverse. And it makes this quantitative. Okay. And then you can just add this in your Newton-Conshorwich theorem. So before here I had norm of df x bar inverse, and I'm saying, yeah, this is too hard, I don't want to deal with it. So I replace this by norm of A, and A now I have some freedom, I can choose it. So maybe I can choose it simple enough that I can actually compute the kappa. And then the only price I have to pay is that I have to prove that A is a good enough approximate inverse. Okay. And then the theorem can be adapted. And one way to think about this is to say, in the end, we only want to apply the contraction mapping. Before it was to this thing, but this is really Newton's method. So it's not only contracting, the x bar is very, very contracting in the sense that the Fréchet derivative of t at x bar is actually 0. It's identity minus df x bar inverse df x bar. So it's not only contracting, it's super contracting. And I have some room to play with. I only want the norm of the Fréchet derivative to be less than 1 to prove that I have a contraction. 0, of course, is perfect for me, but I don't need this. And so I have some room to play with, which allows me to replace this object, which is maybe a bit difficult, by an approximate inverse, which makes my life a bit easier. Okay. But still, I mean, in some sense, I have transferred the problem from df of x bar inverse to finding a good approximate inverse. And in general, it's still difficult, right? If you give me a completely general Banach space and a complete general map F, I'm not able to construct this approximate inverse. But what I claim is that there are at least a class of problem which is large enough to contain many problems of interest within which I can do this. And when I say I, it's not me. I mean, as I said, these ideas, they go way back. I'm just the one explaining them to you today. So we need I to be a good enough approximate inverse and to be simple enough in the sense that we can bound the norm explicitly. And so here is this class of problem for which you can do this. So assume that your f equals 0 problem. You can split it into a linear part, which is indeed invertible and for which you understand the inverse well enough. And then something else, so it doesn't have to be fully nonlinear here. You can keep some linear terms in there. I'm not claiming that L is actually exactly the inverse. I mean, the linearization, sorry. But what I'm assuming is that N is relatively compact with respect to L in the sense that L minus 1 dnx is compact. Okay, and we will see in a moment why this is really a useful assumption. If this is a bit feels a bit abstract, just imagine that you are on a bounded domain. L is the Laplacian and N are some nonlinear terms. Just some nonlinear terms, maybe with first order derivative, but not more. Right. Then it's true that inverse Laplacian times your nonlinear term is going to be a compact operator, for instance. Okay. And so why are these assumptions useful? So remember, the goal is to compute an approximate inverse of df of x bar. And so I have a first candidate, which is L minus 1, because I am assuming that L minus 1 exists and I know it. So let's compute L minus 1 times df of x bar. So this is an easy computation, and I get identity plus this term. And of course, if this was small, I would have won, right? If this is small, then I have a good approximate inverse, but I don't want to assume this is small, because if I'm assuming this is small in norm, it's like assuming the n is small, so I have arbitrarily small nonlinearity or something. Of course, in some cases you can do that, but it's not very general. But the reason this is going to be good enough is because this L minus 1 dn, even though it's not small in norm, it's kind of small still in the sense that it's compact. And because it's compact, we know we can approximate it as well as we want by finite rank operator, which means I only need to perturb the L minus 1 by a finite dimensional thing to compensate for these terms as well as I want, essentially. Okay. And this finite dimensional perturbation is not going to be something crazy abstract or anything. You have a good candidate for this, actually. Right? If you're doing numerics anyway, you're having a finite dimensional projection of your problem. And this one, in principle, you should be able to invert. And this is this invert that I'm going to use this for the finite dimensional projection, which is very natural. So, okay.
So Maxime, can I here ask a question?
Yes.
I just recall myself. There's a so-called N-Frost theorem saying that some compact operator cannot be a limit of finite rank operators, right?
What? Sorry?
Some compact operators it's not a limit of finite rank approximation.
No, this cannot be, right?
There's an N-Frost theorem. There's an example in Banach spaces. Okay, maybe I can.
Yeah, maybe we can discuss it later.
Okay,
but
but suppose this compact operator can be a limit of finite dimensional.
Yes.
Okay. Suppose this is true. Okay, good.
Yes.
Okay.
Yes. So yeah, and then maybe this I skip because it's a bit technical. But once you have this, you have to actually get this kind of estimate. Still, right? So I hopefully convince you that in principle you could construct a good approximate inverse, sorry. But then, and this is where most of the technical work is sometimes hidden, is to get explicitly the delta. Okay. So I'm not going to go too deep into the details, but again, here you have to work a bit, but typically you can get some explicit deltas, and I will show you examples where you can do it. Okay, so how much time? Maybe not so much.
15 to 20 minutes. 15 to 20 minutes.
Yeah. So maybe we start with this population dynamics example, and then we see if we have more time, we talk about something else.
Which one do you like most? Fun? Which topic do you like most?
I like all of them.
Oh, yes, of course. Then population dynamic, for example.
Okay.
Yes.
So yeah, as I was telling to Xiaowang before we started, this is actually the problem that got me into computer science.
Yes, very nice. Yeah.
A bit more than 10 years ago. So here is the model. So it's now called in the literature the SKT model, after the name of the authors who introduced it in the late 70s. So it's a system of two coupled PDEs, where if you look only at the reaction terms, this is just the Lotka-Volterra equations with the sign to say that you have competition between the two species. So I have minus for the UV terms here, and also minus for the UV terms in the second equation. So just Lotka-Volterra equation, but then you want to describe some some spatial homogeneities. So at first you say, okay, let's just add diffusion, standard diffusion, so just the D1. Like you can think D11, D12, D22, D21 are 0 for the moment, and just say, okay, let's add diffusion and see what happens. But actually you can prove that this is not so interesting, in the sense that if you just put linear diffusion, you don't see any patterns, in fact. I mean, in most cases, you can prove that even with diffusion, the behavior of the system is at the limit the same as the behavior of the ODE without any diffusion. And even in the specific cases when something more complicated can happen, it's actually a theorem that all non-homogeneous steady state that could exist, they're all unstable. So you're not going to see them in the long time limit somehow. Okay. So you need something more, and what Shigezada, Kawasaki, and Teramoto, they propose was to add these cross-diffusion terms, which in some sense model some kind of avoiding reaction. So if you see a lot of other people around, you diffuse more. So you're not trying to avoid people in a very, very intelligent manner, but still, okay, you diffuse, and if there are more people, you diffuse more, and hopefully at some point you get somewhere where there are less people. That's what these terms are about. Okay. And as I said, really the motivation behind introducing this system was to observe patterns, and especially patterns where you see what biologists call spatial segregations, meaning that where you have a lot of individual of one species, you have fewer individual of the other species, and vice versa. So they really try to avoid each other, and most of them go into different areas in space. Yes. So here the main object of interest are the steady states of the problem. And so what can we say about the steady state? So the first step, even though this is you have diffusion, you can first look at the homogeneous steady states, the one that make the reaction term vanish. And here, of course, it's easy. It's the standard Lotka-Volterra equilibria, so you have 4 of them. 0, which is always unstable and also interesting. Then 2 equilibria when one population remains and the other one is extinct. And then one last equilibria where the 2 populations coexist, but this one might or might not be admissible, in the sense that depending on the parameter values, these 2 numbers, they could be here, they could be positive, and then it's fine. But some of them could also be negative. And then it's not an admissible solution for your system. Okay. So that's, as I said, that's already a first step, but this is only homogeneous, and we would like, because in experiment people see also non-homogeneous steady states for these kind of problems, and we would like to see them. So that's the main question about this system that was asked immediately when the system was introduced. And it's actually a very interesting but also very hard question somehow. And I've made a lot of studies here. And the main answer is that indeed you can get non-homogeneous steady states, but it's really tricky, and it depends on how the linear diffusion relates to the cross diffusion, but also to the reaction terms. So it's not a super easy answer, but you can find, I mean, this is maybe one of the first paper when this was properly understood, in a sense. But then there are many more papers with many different techniques, which tells you, yes, there exists steady states with patterns, non-homogeneous steady states for this problem. Okay. But even though there is a huge literature, you can find many papers on this. Those papers, they tell you some steady state exists. Sometimes they even tell you a bit what's the shape of it, at least close to bifurcations or something. But they really cannot tell you, unfortunately, the full story. And so let me show you why. So as soon as you do some numerics, you realize that this system can do a lot of complicated things. So here is the first example. So in some sense, in the simpler setting, so all the terms that I grayed out, they are actually taken to 0. So the only nonlinear diffusion term is this one. So what I'm assuming here is basically is that V only diffuses linearly, so it's not impacted by U. At least its diffusion is not impacted by U, but U can react a bit to the presence of V and diffuses more when V is more present. But that's it. And I'm placing myself in 1 dimension also. So make things as simple as I can somehow. And still, if you fix all the reaction parameters to some value which are not so meaningful, and change the linear diffusion coefficient only, then you get this kind of bifurcation diagrams for the steady states. So here on the x-axis is the parameter d, and each point, each blue point on this diagram corresponds to a steady state, in fact. And of course, a steady state is now a function. It's a u and v, so two functions. And I want to do a diagram, so I have to project these two functions. And here the projection is just I plot the value of v at 0. But of course, you could take the norm of the solution and you get a slightly different but similar looking diagram.
And this is a numerical bifurcation diagram?
Yes. Yes. Okay. That was first obtained in this paper by Ida, Mimura, and Ninomiya in 2006. I just, yeah. I mean, this is, I reproduced, I mean, many people reproduced this later, especially me, because I wanted to prove it, but at first it was numerical. And here what you see, for instance, is that if I pick one value of d around here, I can count 1, 2, 3, 4, 5, 6, 7, 8. Maybe there are 10 different solutions that exist for one set of parameters. Mm. And of course, there you're like, how can I prove this by hand, right? I mean, it looks completely hopeless. Yes. I mean, for this system, in some situation, you have kind of a Lyapunov function, and you can use these arguments to say that, but this typically only works in this regime when you have only one solution, which is here. This line here corresponds to the homogeneous solution, this one, which is admissible for the parameter I choose. So then, okay, you can prove this solution exists, but this is just the boring solution that you knew was there all the time anyway. And the more interesting solutions, I mean, of course, close to the bifurcation, you can do things, because at least the primary bifurcation, this is bifurcation from a homogeneous solution. So you can use some kind of Kandel-Rabinovich theorem here to prove that you have bifurcation branches, but then what do they become? And then the secondary bifurcation, it's already hopeless. Yes. So this looks complicated. Yes. But numerically, of course, you can look at the solutions. And here are examples. So in blue, you have the concentration of U, in red, the concentration of V. And indeed, you see this kind of spatial segregation. So weakly, so not in the sense that the support, they are disjoint, but still when you have a lot of U, you have fewer V and vice versa. But yeah, how do you prove by hand? So all the solutions, they are for one parameter value, one set of parameter values. So how do you prove all of them exist? Not easy. So another reason which those results were obtained a few years ago in collaboration with Christian Kuhn from Munich and Cinzia Soresina, who is now back in Trento in Italy. And so what our starting point was that depending on the reaction coefficient, as I said, this homogeneous equilibrium might or might not be admissible. Yes, sometimes this is negative and then it's not admissible. Yet all most of the theoretical results that I know, they use this equilibrium as a starting point, maybe for bifurcation analysis or something. And so they only apply when this is admissible. Okay, if this is not admissible, then all these results, they don't apply. But still, if this is not admissible, it doesn't mean that the system is meaningless. It's just, in the ODE case, it would mean that you converge to one of the two states when only one species remain and the other one is extinct. But this is not like a meaningless scenario. It's one scenario. And then you could ask, okay, if I add cross diffusion, what happens? And then, okay, most pen and paper techniques, they don't tell you anything because the coexistence steady state is not admissible, so you cannot use it as a starting point. Okay. But yet you can do numerics. Those are examples, and they look as nice and reasonable as the previous examples. But okay, how do you prove those are actually solutions from the system? Also hard. A last example, which is maybe less meaningful from the biology, but more of a mathematical curiosity, let's say. Still, I find it interesting. What if the D1 and D2 are actually negative?
Oh.
Of course, I'm not claiming this makes a lot of sense from the biology, but from the math, it's an interesting question, because then potentially, at least if U and V are really small, then you get a backward diffusion equation. So this is ill-posed, I mean, all kind of things that happen. But if U and V are not so small, it could still be well posed. This time I'm not assuming that the D11 and so on, they are all 0. All of those, they are positive, these coefficients. And therefore, even if D1 is the negative, if U and V are not all very small at the same time, this could still be well posed. But of course, it's hard to, because then you have to know in advance what happens with the solution. And this is really hard mathematically. But still, numerically, you can try and find solutions. And yeah, and again, you find reasonably looking solutions, which are smooth. And I mean, those were computed using, because it's Neumann boundary condition, you can just use a cosine series. And you look at the decay of the Fourier coefficient, it's really nice decay. You think this is a reasonable solution. But again, mathematically, you have this negative linear diffusion coefficient in there. Not so easy. Okay. And what I claim is that all the solutions I showed you numerically, actually, it's not so hard to use this computer-assisted proof to say they exist. And not only to say they exist, but to say that what you see here is actually the true solution, maybe up to 10 to the minus 10 or something. And therefore, in particular, the qualitative behavior of this, a lot of U and fewer V and so on, this is really what is happening in the solution. Yes. So for that, as I said, you can start by using a Fourier series for the numerics. You don't have to, but since you have a non-boundary condition, it's one natural way of doing numerics for this. And you get an approximate solution, which is just a truncated Fourier series. So, I mean, trigonometric polynomials for U and V. And in that case, for instance, if you think a bit about it, if U bar and V bar are trigonometric polynomials, and you plug that in the equation, then all of this is just a trigonometric polynomial of twice the degree. This as well, then applying the Laplacian to a trigonometric polynomial is also not trivial. And then indeed computing f of U bar V bar is not so hard in that case, for instance. Okay. You just have to do it with interval arithmetic to be careful with the rounding error, but that's basically it. So this is not the big problem. What is a bit more involved is the computing the approximate inverse. Because typically, as I told you, at least for easy cases, you want the L, the part which is invertible and which is easy to invert, to just be the Laplacian. But if you do just take for L the Laplacian or the linear diffusion, then you still have the non-linear diffusion term left. And so this is not relatively compact with respect to just linear diffusion. So you get into trouble. And so what you have to do here is to be a bit more careful with how you define the approximate inverse. And so the approximate inverse, what you have to do here is take the Laplacian pre-multiplied by something which is essentially the inverse of the diffusion matrix that you get inside. Yeah. And here, after you do that, it's not so hard, but I'm skipping details to show that an approximate inverse built this way is a good approximate inverse, and you get the estimates. Yes. And then you can apply the Newton-Kontorovich argument. And for instance, this is what you get. So those are the solutions I showed before when the homogeneous set is not admissible. But yet the computer-assisted proof, you can apply it. And then it tells you, yeah, this is actually a true solution up to an error which is 10 to the minus 10 in C0 norm. So C0 is not actually the space we use for the proof, but it's just the norm we use is stronger, and it's easier for me to state the result that way. Okay. And if I can do this for this one, I can do it for the other one. It's the same. I get similar results. And of course, I could do it for the bifurcation diagram, or at least it's very straightforward to do it for a discrete version of the bifurcation diagram. And so here, all the blue dots are now validated solutions. Okay. So in some sense, I validated part of the bifurcation diagram. And here, the natural next step, and this is something we're actually currently doing with Olivier, is to do not only a discrete version, but really to do the entire curves properly. And one advantage of doing that is that if you do the entire curve, you can also prove that you didn't miss bifurcations. Because at the moment, I proved that all these solutions that are there, but I cannot prove that here in the middle, there was not a pitchfork that I missed numerically or something. But if you really validate the entire branch, because of the local uniqueness result of the contraction mapping, then you get a proof that you didn't miss branches that bifurcate out. Okay. And maybe it's already over time, so I stop here and thank you for your attention.
Thank you. Oh, thank you very much, Maxime, for this very clear, comprehensive talk. Indeed, I have listened to previous talk on CFP, but you are the first one to really illustrate how to do this interval arithmetic, to illustrate why this is a very bad examples. I mean, very clearly. I appreciate it very much. Very nice, very nice. Very good talk. So, okay, so please, any comments, questions from the audience? Just unmute your microphone and ask. Maybe let me start from a question like, so I mean, we can check Wikipedia, but there's a theorem saying, consider separate Banach space. There exists complex operator, which is not a limit of a finite rank operator. So this is not necessary. But a limit of the finite rank operator must be compact. So it's not if only if. So,
okay.
So I was thinking maybe we are very lucky because we consider elliptic systems relation diffusion equation. So this property always hold. So we choose L1 space, L2 space. But I think that kind of statement is not always true. Okay. I mean, this is just remark.
Okay.
Yeah. So I will send this Wikipedia webpage or some keyword to Olivia and you check.
You can send it to me. Yeah. Thank you.
Yeah. And also, this is also related to the approximation because you want to construct the approximative inverse by this finite rank property. And usually this happens, I think this does not happen when you consider hyperbolic equation, right? Like, you know, like this wave equation, Einstein equation, now, you know.
Yeah, then you don't have the compactness. Yes.
Yes.
Yeah.
Yeah, the issue is the compactness and also regularity. So in this sense, I mean, because then how do you use CAP to solve this setting like wave equation hyperbolic systems?
Yeah, you don't. I mean, that's the main reason why there are many computer-assisted proof for elliptic problem. Yes. There are some computer-assisted proof for parabolic problem, but as far as I know, there are very, very few for hyperbolic problem. It's much harder to use these ideas. So I don't think there are not any, but if you want to use this kind of approach, then for hyperbolic equation, it's much harder. I mean, indeed, because this compactness is kind of, you can reinterpret it as a smoothing properties, which you don't have for wave equations or something. And then, so it's clear that this is, you cannot do everything with this approach. Okay. And hyperbolic equations are, I mean, it's hard.
Okay, I see. Because I was also thinking like this, you know, this finite rank stuff is pretty like a Galecki approximation, right?
Yes.
When you have PD, you want to prove the existence of weak solution, you have Galecki approximation, and then you take limit, and hopefully you have a compactness. I think this kind of method apply for parabolic equation, also wave equation sometimes. I am thinking maybe, I don't know, there's still some space to adapt this CAP to hyperbolic equation, but I don't know what lies. So do you think maybe there's the third approach to construct, to estimate the inverse of a DF? Do you think there's a possibility? Or only this spatial method, like, you know, spatial radius, rule, right? And also this A, are there the third one? Is there the third approach? Do you think?
Yeah, I very much hope so. But that's also why I'm happy to talk with other people, because I'm getting too used to this. So I'm always thinking, yeah, this is what I have to do. And so it's nice to have, I mean, you know, people who are not super familiar with this, they immediately think, yeah, maybe we can do this differently. And then it's good. I don't know how to do it differently. But I very much hope that people can have ideas for that. And I mean, maybe not as generally, because this is, as I said, very general, but for some specific problems, maybe hyperbolic one, maybe you can find a good idea about how to build an approximate inverse. Right?
Okay, okay.
That would be very interesting.
Yeah, thank you, thank you. So other questions, comments, remarks? I am so curious. Can I ask another question?
Sure.
I am so
Sure.
curious.
Yeah.
I don't know whether this question is nasty or not. I have a feeling that for CAP, now you have a numeric, then 99% of the case you can prove the numerics, right? It's if now suppose now I have a numeric solution, but in the end, I use CAP, but I cannot prove this numeric, then what happens? If I cannot prove this numeric, then what are the typical situations?
Yes. So there are two. Sorry. Maybe we can go back at the. So typically, if it fails.
Yes.
Oh, let's look at the more general theorem. This one. Yeah. Depends where it fails, and then depending where it fails, it tells you something already. So what can happen is that you cannot prove that your approximate inverse is good enough. Yes. And maybe this you have to investigate a bit where the problem comes from. But it can be that in the finite dimensional part already, A is in fact super ill conditioned or something. And then what this would tell you is that you're probably close to maybe a bifurcation or something, right? If I go back to my bifurcation diagram, and I try to apply the computer-assisted proof very, very, very close to bifurcation points, then it will fail. Yes, because it's supposed to tell me that I have locally a unique solution, and if I'm arbitrarily close to the bifurcation point, this is not true. And this will not be because the approximate solution is bad. The approximate solution might be fine, but this will be because the problem is getting degenerate, and you will notice it here. On the other hand, what can also happen is then, even though you think you have a good approximate solution, right? Because for instance, you do Fourier, so you truncate everything. When you compute the product, you're not actually going to, if you have a trigonometric polynomial and you compute the product, it should have twice the degree, but numerically you truncate everything to a fixed degree. And you think, yeah, this is fine. But then when you actually rigorously compute everything for the residual error, then you notice, oh, this was actually not so small. And then maybe this can also happen. But I mean, there is a very nice, it's an old paper. I don't exactly remember from when, but an example probably from Rump and maybe Plum together when they find these spurious solutions using finite elements for an elliptic PD. When they have a solution, it looks nice. You refine the grid, the solutions still look nice, but they prove using this that there is actually no solution. It's really a spurious solution. And then when you look at the approximate solution, you cannot guess it's crazy or anything, but when you actually try to compute things, and in particular to compute the residual error, you realize it's not small.
Okay. Yeah, I am curious about that paper. Yeah. So can I summarize okay, suppose the CAP fail to justify or validate the numerical solution, then either I can say maybe I am near the bifurcation point, some bifurcation point, or my numerical solution is not good enough. Right.
Yes.
I see.
And so, okay, if you're interested in that, I mean, one thing you could do, because when you get all these estimates, in the end, what you prove is that this fixed point operator, you take a ball close to the numerical solution, it's mapped into itself. Yes. But actually, yeah, by doing that, you say, okay, I take the ball and I control where it's mapped. And so, if that's the case, that there is no solution, probably you can prove that the ball is mapped completely outside of itself, just by using similar estimates. Right? You compute the t tilde at the numerical solution, you see where it goes, and then you control nearby solution. And indeed, if you prove that the image of the ball does not intersect itself at all, then you also have a proof that there is no solution in the ball. If there was one, there would be a fixed point.
Oh, okay.
That's really a way of proving that your numerical solution is nonsense.
Nice, nice. Cool. I see.
Which is again not very likely, but sometimes I mean, at least you can build examples for where you can construct these things.
Yes, yes, yes. Nice. Thank you. And yes, please comments. I have now 2 more questions, but I have to wait for the audience. Okay. Yes, please. Okay, interrupt me if you have questions. Olivia, do you have any questions? No. Okay. So now I have I think this question is a little bit more general concerning this population dynamic. Okay, you have 2 equations. Now there are a bunch of people who study this EFT system. Okay, maybe not close diffusion. Okay, but Lotica for Terra, for example. And if you have 2 systems, usually you have what? Comparison principle. And some people use variational method to prove this. So suppose you have some variational structure. But if I understand the CAP correctly, your methodology, construction maybe the construction of the approximated event are totally independent of this comparison principle variation structure. Right? This is my first question. And now my second question is, suppose you know there's additional structure like a comparison principle or variation structure. Will this structure make your CAP analysis easier?
Sometimes, but not always. For instance, for this problem, if you look at where is it? This case, which is called the triangular case, because there is no cross diffusion for V, only for U. Mm-hmm. This one indeed mathematically is simpler because at least for V you have a maximum principal argument and this kind of thing. Because for V it's really yes, and so mathematically this was simpler. And then we thought, okay, for the computer-assisted proof it must also be simpler. But in the end, so I first studied this problem. But it turned out, so I had one solution which was only working in this case, but it was actually more complicated than the solution for the full case. So
really?
Not always, not always. But of course, I mean, in some, let's say in Hamiltonian dynamics, when you have conserved quantities or something,
yes,
those are information that you need to also take into account in the computer-assisted proof. So sometimes really you need to use this information, but it depends a bit. Variational structure, as far as I'm aware, it's often not used by computer-assisted proofs.
I see. Okay, now I understand. Because if I have a Hamiltonian system, so this is a conserved quantity, you need to encode this conserved quantity into your F, right? Zero finding problem. So this is kind of like a constraint. So yes, but like a variational structure or comparison is an inequality. It's not in the zero finding problem. So you just care about how you write down this F, right? Not mathematical structure that has an effect of your F. Okay, I see. Cool.
But still, right? I mean, of course, you have to understand it. This is not magical, this computer-assisted proof, right? So you have to still understand the equation to some extent just to set up the problem correctly. I mean, sometimes the way you write down the F, for instance, is informed by what people know about the equation. And it's not like I can come here, know nothing about the equation and immediately do a computer-assisted proof. I mean, in some very easy cases, that's true. But in most cases, you need to understand a bit the equation. It's not it's really complementary with usual pen and paper techniques.
Yes. Also, Olivia is yes, but okay, because my in our club, I have a feeling that he just need a equation, need a numeric solution, and then he can do everything without understanding other, mathematical structure. I mean, amazing. I would say CAP is currently, at least currently for me, it's like a magic, yeah, really. But no, but I am not expert. I should borrow. Okay, yes. So my face is upside down, but like a magical or not complete magical.
No.
Okay.
Yeah. But hopefully, if Olivier can, transfer some knowledge, and then you see it's not so magical. But at least for the other, you can pretend you do magic.
Okay, so answer other questions. Now, let me ask another question. Now, suppose I'm a PD guy, okay? Whatever existence, of course, the next question is about regularity, okay? Like
Yes.
a weak solution, classical solution. I have a feeling that in the CAP setting, Banach space, of course, there's an issue of choosing Banach space, but there are some PDEs, they are very, very, very fragile in some sense, like they don't have they have like for example L2 solution, but they don't have a H1 solution, for example. In this sense, then, so if you don't know this, and so CAP cannot find solution, right? Because a priori there are no such solution. You have to choose the correct Banach space at the very beginning, or you can just give a Banach space and then like L1, because Olivia told me he likes L1, always L1. Okay, now you choose L1, and then if you do something and in the end this suggests you something, so I'm not sure. Okay, how should I formulate my question? For some PD, if a regularity is very important, how can you encode such concept in your CAP problem?
Yeah, so there are two things. First, indeed, you don't need to know a priori what's the regularity, but you need to make an informed choice for your Banach space. And then in the proof, if the proof succeeds, then you have proven that you have the regularity which is associated to your Banach space a posteriori. That's fine.
Okay, now I have a concrete example, but this is not relation diffusion or elliptic. There's a Boltzmann equation, okay? Boltzmann equation. Consider linearized Boltzmann equation and dynamic near equilibrium. There's a result saying they have a C1 solution, but they don't have a C1 alpha solution.
Okay.
So I mean, but if you don't know this, and how do you find solution?
Yeah, exactly. So that's what I said. If you don't know anything about the equation, you try to do the computer-assisted proof in a very regular space, and then it fails, of course.
Fails.
So that's where you will just for instance, probably the residual error will already be large because actually the solution does not belong to that space.
Okay, I see. So then you still need to talk about the expert, pure mathematicians, and about what they suggest.
Yes, but they also sometimes they confuse you. They say you have to explain them carefully what you want to do, because let's say Navier-Stokes. Of course, Navier-Stokes, I didn't show you the examples, but you have a computer-assisted proof for Navier-Stokes, for which regularity, of course, we don't know yet.
Yeah.
In general, but we don't know the regularity for, let's say, arbitrary initial data. What we looked, we didn't do the Cauchy problem for Navier-Stokes. We looked for periodic solution in Navier-Stokes.
Periodic solution.
And then periodic solutions, they are way more regular than your typical solution, right? Because you exist forever, and then this gives you regularity. So then for Navier-Stokes, actually, even though it was Navier-Stokes, we could do the computer-assisted proof in a very, very regular space, like analytic function, right? And it's not, it's just typically when you do this, what I said at the very beginning, that we care about specific solutions. Most of these specific solutions, they have way more regularity than your average solution. And this is also one of the reasons why these computer-assisted proof they are successful, is because we are specific solutions that are much nicer. I mean, at least from a regularity point of view. Of course, from a theoretical mathematician, you tell him, okay, I need a periodic solution somewhere in Navier-Stokes. He will tell you, oh, this is very hard.
I see.
For us, it's easier in the sense that this will be way more regular.
I see. Cool. Okay, I'm very satisfied, happy.
Well, thank you for the question. I mean, it's always a pleasure to talk about this.
Yes. Okay, now I think so. Audience, from the audience, any comments, remarks, questions from the audience? Okay. I think if this is not the case, then I think that's a thank our speaker, Professor Maxime Breden again. No, thank you. Yeah.
Thank you.